All right, kids, so here's a problem number 25 at the bottom of page 4. And so they graph this function, or this surface, I should say. So it's x squared minus y squared. And I should probably zoom in so it's looks a little better on the screen. I hate when I do that. I've just kind of messed up my orientation. I'll never get it back again. So they want 25 grid lines in each direction. So I'm going to change the number of grid lines to 25. And so each direction has 25 grid lines. So the question is, what do all 50 of those curves have in common? Confirm that the line through 1, 1, 0 and negative 1, negative 1, 0. So it's starting at 1, 1, 0 and going to negative 1, negative 1, 0. So what I'd like to do now is I'd like to introduce a space curve. And so a space curve is a parametric function. So this is going to start at 1 and it's going to go to negative 1. So I'm going to subtract 2t. T is my parameter and t is going to vary from 0 to 1. A lot of ways to do this, but the y value also starts at 1 and will go to negative 1. So I'm going to subtract 2t again. And the z value is always 0. It stays 0. And so I want the t value to go from 0 to 1. And so at 0, I am entirely at the point 1, 1, 0. And as t goes to 1, I'm at the point negative 1, negative 1, 0. And let's turn that graph on, and there is that line. That's kind of cool. That line is there. How would you convince yourself that it is entirely in the plane? And there's probably another line. You guys should probably try to graph the other line. There's another line that's also kind of like that as well. And so let's see. And ooh, there's another line through the origin 0, 0. The y is entirely on the plane. That's part C. Identify it and find it and graph it. So you can do that. Let's see. Part D. Find an equation for the plane that is tangent to the surface at negative 1.5 and 0.75. So I'm going to go up here and I'm going to plot that point. So I'm going to plot that point at negative 1 and positive 0.5, excuse me, 0.5. And so there is that point. It's right up there, kind of on the very edge. And I can display a tangent plane at that. So let's see, not the tangent line, not the derivative trace, not hide all objects. Here it is, tangent plane at the point. So there is that plane. What I'd like to do is I'd like to find the equation of that line. So what I'd like to do is find the directional derivative kind of going off in both directions. So I'm going to hide that plane. I don't want to show that tangent plane anymore. Oh, I probably got to get rid of it by clicking down there somewhere. No? Interesting. I would like to get rid of that plane, but I don't know how. But anyway, that's okay. So let me show the partial derivative with respect to x at that point. I'm curious to see if it gives me a value of that of the slope there, because if I knew the value, then I could begin to write the tangent plane. And so that's kind of the problem. I don't see a way to capture the value of that slope in the x direction on that line. So that's what you can do in GeoGebra. I can do that because it describes a function for me. Same thing if I do the partial derivative with y. Again, I don't see anywhere on the graph where it's displaying to me the value of the derivative. So I may go back to GeoGebra and solve this problem there.